Theoretical Physics at the State University of São Paulo, and also the South American Institute for Fundamental Research, which is an ICTP institution. And this is the institution that is hosting this workshop. So I'm one of the organizers, together with Clara Dvorky, who is here from Harvard. She's originally from Argentina. Nelson Padilla, I don't see Nelson yet. Here. From the Catholic University of Santiago, Chile, and Miguel Quartin from the Federal University of Rio de Janeiro. So it's great that we had almost 300 registered participants. I want to thank them all and thank all the presenters. And we decided to try a different format this time, focusing on discussions based on pre-recorded talks. So this is a format that I haven't tried before. It's based on something that happened, I think it's called Cosmology from Home or something like that. So it's more demanding. It's more demanding to the presenters because they have to pre-record a talk. It's more demanding on the audience because they have to be more proactive and look and watch for the talks and make sure they understand or make questions, etc. So yeah, so we'll see how it works. But this also allows for something that became popular lately, binge watching. So instead of binge watching a series on Netflix, you can binge watch this fantastic series of talks. So I really recommend you to do that. So this format allows for a light program. So we have the aim is to have 2 hours of discussion per day, 1 hour in the morning Brazil time, 1 hour in the afternoon Brazil time. Of course, I don't want to be very strict on this time, but we'll see how it goes. So the idea is that each session will start with a very short, maybe 1 slide if you want, from each of the presenters of a talk. And then also for the people that are presenting posters, they just open up their cameras and say who they are, so we know who they are and ask questions. Also for the posters, they were very good posters, by the way. So I'm sure there will be glitches, and I want to apologize in advance. Some glitches are our fault, but if Google crashes, like it happened this morning, there's nothing we can do. So for a few minutes that looked like an eternity to me, I was desperate because everything crashed. So we had no program, no nothing. I don't know if you noticed, but it was terrible. So anyway, so the Zoom conduct code is that people are not talking are muted, of course. And if they want to ask questions, they raise their hands, and the chair, in the case is today's Pedro Ferreira in the morning, we'll call the questions, and then the person unmute and ask the questions, and then the presenter who is asked this question to will respond. So one of the goals of this workshop is to involve more people in Latin America in observational cosmology. As you know, many of the cosmological experiments are located in the region. And we already have groups in Brazil, for instance, working in ES, ESI, LSST, JPAS. In Chile, there's a group working in LSST. Argentina has a group centered in a CMB project, Cubic, that we're going to hear about. And Colombia has a group in DESI. So we need to have more people in Latin America working in observational cosmology. Finally, I want to acknowledge that this has been a very difficult year for the world as a whole, and also that this is the last working week of the year. You know, next year is Christmas. So I do hope that we can discuss the exciting works that were pre-recorded in a congenial, informal, and pre-holiday atmosphere. So please do enjoy, and I pass now to the chair of the morning session, Pedro Ferreira. Pedro.
Thank you, Rogério, for your introduction, and thank you for inviting us all to come and give these talks in this novel format. And so I have been instructed that the way we are going to do this is that to start off, each one of the speakers has a minute or two to talk about their talk without giving it. Then I'm going to ask the poster presenters to each flash up their posters on the screen. I assume you've made them co-hosts so that they can show their posters.
Oh, sorry, Pedro. The idea is not for them to show the posters, to flash the
No?
posters. They can do it afterwards, but just show
Understood.
themselves and say,
Show
look, I'm
themselves.
this
You need to
person.
show yourselves, and you need to tell us what your posters are about. Again, in a very short, and then we will open to questions. So we are going to start off with Martin Croce, who is going to tell us, I think the title is wrong on the webpage. It's Galaxy Clustering in Imaging Surveys, not Imagining Surveys. DES as a case example. So Martin, tell us. And I assume you can unmute yourself, yeah.
Yeah, I don't remember the title of my talk, honestly. But anyway, so can you hear me well? Yes.
Yes.
Perfect. Okay, so first, let me thank Rogerio, Cora, Nelson, and Miguel for putting this together. I think it's great that we can do conferences, no matter the situation in the world is, and it's great that we can get together to do this. And in particular for South America, no? We all have our hearts there. So as regarding to the talk, the main motivation for the talk was that, so in the past couple of years, we are seeing this emergence and establishment of this new major player in observational cosmology, which is imaging surveys or weak lensing surveys, right? With DES, KITS, HSC, and in the future, they will even play a larger role with LSST and UPIT, as Roger said before. And so this will do cosmic shear basically, but the best way to profit the best from this service is to combine cosmic shear with galaxy clustering, and to cross-correlate shapes and positions of galaxies to do galaxy lensing. So to do this combination of proofs, galaxy clustering, cosmic shear, and galaxy lensing. There are different ways to do that. But I try to focus on the galaxy clustering part of that combination, and in particular in the three things that I believe are the most important going forward in the future to do clustering in this kind of service, which is besides how we measure the correlation of positions in practice, is how we identify and mitigate observational systematics, because these surveys are very susceptible to imaging conditions that they vary across the moment where the data was taken. So how do you mitigate observational systematics? How you can define optimal samples in the same way you do in a spectroscopic survey that you define CMAS or LRGs or so, how you can do a similar thing for imaging surveys. And the last thing that is much more important than we thought it was going to be a few years ago is how you estimate photometric redshift. No? So that's going to play a critical role in the future. It's playing it now and will be more so in the future. So I try to cover those three things, and those you can find in the talk, and I'm happy to discuss more about it.
Okay, thank you very much. Right, we will now move, this is the quickest conference I've ever been at. We now move to Jorge Norena, who will tell us about learning about inflation from the 3-point function.
Yeah, so first I want to make a clarification. So I decided to give a sort of review talk because I thought it would be more useful for a Latin American audience. But the conference is very diverse. It includes not only Latin America, but world-class experts. So I apologize. I thought it would be more Latin American, and I thought it would be more useful. But I focused on mainly three things. So if I can share my screen quickly. Yeah, so what we learned about inflation, we know that we can learn by looking at the squeeze limit of the spectrum, we can learn about the number of fields present during inflation. So it makes sense to look for local type non-Gaussianity, makes lots of theoretical sense, because if you observe it, you would have seen that inflation was multi-field. I then asked the question whether LSS can improve on the CMB, and the conclusion is that, well, there's not yet a thorough study, in my opinion, but some preliminary results. This was done, for example, in position space, rather than redshift space, the plot that I'm showing. They showed that it will be hard, and it needs a lot of work going to smaller scales and maybe new techniques. I discussed a few of them that people have been looking at in the literature. And finally, if we do achieve to get to FNL of order 1, which would be very nice, but it looks a bit, well, it would be very nice, then you have to care about relativistic effects, and there are lots of people working on the bispectrum with relativistic effects. There are even numerical simulations and some results that I had with my group. I presented very briefly. Yes, so that's it.
Thank you very much. That was very efficient. Do you want to unshare?
Yes, I'm trying to go back to, yes, okay. Thanks.
Very good. So we now move on to Oliver Friedrich, who will talk about a way beyond 2-point statistics in the analysis of large-scale structure.
Yeah, thanks a lot. Hi, everyone. I'll also just quickly share my screen and show you 2 slides from the talk. And yeah, first of all, again, thank you very much to the organizers for having me. I think this can be a really fun event. And yeah, so my talk is about one potential way beyond 2-point statistics, and this is studying the full shape of the full distribution of cosmic density fluctuations. And yeah, what you see here on the right-hand side of this slide is on the y-axis, you see lensing convergence, in this particular case from lensing of the cosmic microwave background. So this axis, you can think of something like matter density. And then on the y-axis, you see counts of galaxies in some aperture, in this case, 30 arc-minutes on the sky. In the talk, you find more details about what kind of redshift ranges and whatnot. But basically what's shown here in the color map is a model for the joint distribution of the two that you would expect when you look at the sky. And so the most robust way that we currently have to extract cosmological information from the large-scale structure is via what Martin just mentioned, 2-point statistics. But 2-point statistics are quite a strong compression in some cases of what's actually going on in the density field. For example, in this particular case, 2-point statistics, if you fix it to one particular smoothing scale, it just extracts the second moments from the distribution. So it would extract the variance of galaxy density fluctuations, variance of matter density fluctuations, and their covariance. This would basically be the 3 times 2-point analysis that you sometimes hear about. And yeah, in this project, we are trying to push this forward to get rid of this massive compression of data and analyze the full shape of the distribution. And yeah, if you have a look at my talk, what I'm first of all trying to do is I'm going to show you that the kind of theoretical modeling that we apply to do this can actually be understood in steps that are quite analogous to what you're typically doing in 2-point statistics. And then I'm also showing you some examples. Yeah, here you see on that slide a comparison of our model prediction, which would be the blue line, and here the orange dots would be measurements of the full PDF of density fluctuations in n-body simulations. Even subtle effects can be understood from this. For example, here I show you how the PDF reacts to different types of primordial non-Gaussianity. And again, the dots show measurements from simulations, and the line shows you analytical predictions of that. By the way, sorry, I was trying to share a different slide, but no, never mind. But anyway, we can do these kind of things. And what I particularly point out in this slide is that we have public code out there. So if you look at, for example, the last slide in the talk, then you find a link to a GitHub repository where you can find where you can carry out theoretical predictions that tell you about the shape of the PDF yourselves. And yeah, that's it.
Thank you very much, Oliver. And finally, from the speakers, we have Joseph Curvilla on 3-point Gaussian streaming model and the cosmological information content in 3-point velocity statistics.
Hello, everyone. I hope you can hear me. Yeah, I'm Joseph. I would also share my screen. Yeah. So in line with what Oliver mentioned, this talk is also about going beyond the 2-point statistics for the future forthcoming galaxy redshift surveys. So far, for the configuration space clustering analysis, it has mainly been used the so-called streaming model, which was put forth by Peebles in 1980s. In this work, in this talk, I want to share about my work, where we generalize the streaming model to endpoint statistics. So basically, there is a way to map the endpoint anisotropic correlation function in redshift space from the isotropic correlation function in real space. So it turns out there is a simplistic approach, and this is exact, with the approximation of the distant observer approximation. And we were able to obtain a phenomenological model when we specified for the 3-point, whereby we substituted the velocity distribution, which was required with a Gaussian distribution. And the blue line here, for example, is a model prediction, which we show with the measurements from the n-body simulations in orange points. On the y-axis is the spherically averaged connected 3-point correlation function. So as you can see, on the larger scale, the model seems to work well. And this gives us a way to, in the future, for forthcoming surveys like DESI or Euclid, to make use of 3-point clustering analysis in a easier way, at least the theoretical side. And then basically, we also found that this is able to help some form of degeneracies, as has been mentioned in some other talks, which I've listened to already, that the use of 3-point clustering information. So for moving away from clustering, we also wanted to focus a bit more into the velocity statistics side, because this introduces a higher order relative velocities. And we quantify this velocity information using Fisher matrix formalism and use the Quixote simulations to compute both the covariance matrices and the derivatives directly from it. And we were able to find that this 3-point relative velocities were able to obtain substantial information gain over the pairwise velocities, which has been presently employed in peculiar velocity surveys and kinetic Zunier-Zeldovich experiments. So this gives us a way forward to use higher order relative velocity statistics in KSE and peculiar velocity survey. Yeah, thank you for listening. Yeah.
Thank you very much. We now move on to the poster presenters, and we're going to start off with Caroline Gwendoline, and she will talk about relativistic effects in the halo 2-point statistics.
Okay, so hello everyone, and thanks for the organizers of this event. So I'm not going to show my poster, I'm going just to say hello. And my talk was about the trying to detect the relativistic dipole on the cross power spectrum of halos in the G-evolution simulation. So that's it, thanks.
Okay, thank you very much. We move on to the next speaker, which is Guilherme Brando Oliveira, and relativistic effects in the growth of structure.
Hi everyone, thanks for the organizers for the event. My poster was on relativistic effects on the growth of structure. We just introduced a way to compute, to turn Newtonian simulations into relativistic ones in a fast and computationally low cost way. So if you're interested, please check my poster. It's only 3 minutes, and thanks everyone.
Thank you very much. Then we have Henrique Rubira, the effective field theory and perturbative analysis for log density fields.
Hello, everybody. I'm a PhD student at DESI, Germany. And yeah, I did this work in collaboration with Rodrigo. It's about constructing an effective field theory for the log transformed field of density. So in principle, with the log transformed density, you can bring information from the higher order n-point function down to the 2-point function. And we analyzed this scenario and constructed a consistent perturbative approach for it.
Very good, thank you very much. And the final poster is by Tiago Mergulhão, and it's the effective field theory of large-scale structure and multitracer.
Yes, hello everyone. Can you hear me?
Yes.
So in this work, we are trying to see what happens when we put together the ideas of multitracer and perturbation theory. And we would like to check if when we try to recover cosmological parameters using the 2-point function, using also the multitracer technique, you can lower or we can decrease the error bars that we got. And that's basically it.
Thank you very much. Very good. Those were the presentations. We are 20 minutes into this hour. I open the floor to questions, and let me remind you of the etiquette. The etiquette is you put your hand up, and I see if you put your hand up and let you speak. So I am scanning. Aha, Miguel, go ahead.
let's break the ice, right? So we have to give some quick start. So I have a question for Ferreira. So I was trying to understand your talk about, using the full shape of the PDF. And I'm trying to see, because when you start your talk, you start by showing a plot of delta G and delta M, right? The galaxy and matter. And basically saying, well, let's take the full shape of the PDF. So I understand this as, let's not use a linear bias only, right? This is just a bias model. I didn't see you talking too much about bias itself, but I think that's what's behind your idea, right? So instead of putting a bias, I use the full shape of the PDF. So, but how does that work in practice? I mean, I cannot use then all the redshift space distortion machinery, right? Because they all rely on having a number there, bias. So you have to rework that from scratch. Is that I'm understanding that correctly?
So yeah, I think so. So first of all, I should say that most of the stuff I was referring to is actually in projection. So this would be in photometric surveys like DES, like Martin was mentioning in the beginning. That means if you were to push this to actual data analysis, you typically wouldn't look at the 3-dimensional density field. And typically in photometric surveys, the redshift bins are going to be so wide that you're going to project out any redshift space distortions anyway. But what you're, of course, referring to in terms of bias is quite a significant problem in this whole thing. And let me just quickly share my screen again. 1 second. I'm going to try to be more clever this time. If you look, for example, at this figure, so here you see this is in n-body simulations. We have this buzzard n-body simulation map of dark matter density on the sky. This would be the x-axis here, and then on galaxy density on the sky, this would be the y-axis. And in a sense, well, you see the joint distribution of the two here, right? And you see a clear correlation between the two. And now linear galaxy bias would just be basically tells you about the slope of this ellipse, if you will, right? So the expectation value of delta G given delta M in a linear bias model would be B times delta M. But on top of that, well, there's 2 ways on how you can make this more complicated. First of all, you're not expecting this this relation to be perfectly linear. So at some point, you're gonna, for example, expect more, maybe something of a banana shape here, which would mean a quadratic bias. But what you also see is that on top of this expectation value, you have some scatter. So there is some stochasticity between galaxies and matter density. And this you also have to model when you model the full shape. And the most trivial assumption would, of course, be Poissonian shot noise. But what we actually found when looking at simulations is for certain types of halos, this actually doesn't work well. For example, you may find super Poissonian shot noise, and the level of shot noise might also depend on the overall matter density field in your environment. So there are complications when you're trying to model the scatter, and this is actually I think the biggest complication with respect to 2-point statistics. But given
did you mean to say that this extra stochasticity is coming basically because you have a large photo Z errors? Is that what you understood from what you said? No, this is there anyway, right? Yeah, exactly. Yeah. For that, fortunately, I was kind of expecting that this question might be coming around. So I already opened this figure from one of our papers. This is me and others in 2018. And what you see here, for example, this is from the buzzard simulations. And in the buzzard simulations, we have galaxy density maps on the sky and matter density maps. And you see here, as a function of matter density in a certain aperture, you see the variance of galaxy counts in that aperture divided by the average value of galaxy counts in that aperture. And this ratio should be exactly 1 if shot noise was Poissonian, right? But you see here, at least in the simulations, we find significant deviations from that. So first of all, you have super Poissonian shot noise for that particular type of halos. And then the super Poissonianity even is a function of matter density. So this is actually, a big complication of this model, which I didn't even get to talk about in the talk. But yeah, this is something that we're thinking about, and we have some parametric models to add this to our analysis. Yeah. Thank you.
Mm-hmm. Okay, any more questions? So
I cannot raise my hand because I'm a host. But I just want to ask Oliver, what are the free parameters that enters into your modeling, Oliver?
So, for example, let me quickly go to my slides. So in this figure, you see some of the free parameters. This would be omega matter, sigma 8, then linear galaxy bias in this in the simplest possible approach, and then you see a parameter which is called R. And here we have an approach where we say, let's imagine there is some auxiliary field which is something like a smooth galaxy density contrast, and then the actual galaxy counts are something like a Poissonian tracer of that field. But then we allow for an additional stochasticity between that smooth field, of which the galaxies are perfectly Poissonian tracers, and the underlying matter density field. And that stochasticity is described by a correlation coefficient R, and this would be this R that you see here in these contours. And the funny thing is, if you allow for this R to be smaller than 1, then it turns out, and for that, let me just share the other figure again. It turns out that you can, with a certain choice of R, you can exactly describe this kind of behavior of the slope of this super Poissonian ratio that I talked about before. So here, for example, the blue line would be exactly a model parameterized by linear bias and this kind of correlation. And you see this actually manages to describe shot noise quite well in that situation. So that would be the two the most important free parameters. And in principle, you can go further. Just showing one more slide here. In this slide, you see we vary one additional parameter, which would be now FNL, because in this PDF, since it's such a rich information, this two-dimensional plane of data, basically, you can constrain quite a lot of parameters. For example, you can start to even look for primordial non-Gaussianity in the initial PDF. Of course, well, from that figure, you see this is not competitive at all, yeah. But yeah, just pointing you here also to the fact that in part, this is actually because in this analysis, we assumed quite a long redshift range. And it would actually be nice if we could also do this in 3D with spectroscopic data, then we could constrain much better, even these kind of things.
Mm-hmm.
Thank you.
Very good. Bruno Moraes has a question.
Hi. I wanted, well, let me just, for those who don't know me, I'm a tenure track professor at UFRJ, Rio de Janeiro since 2019. Some of you know me from when I was a postdoc at UCL a few years ago, and then I had a stint outside academia. So just so you know who you're talking to, nice to see you all. I wanted to ask Oliver a question, and then Miguel's question made me complicate my question. So it's a two-part question, if that's okay. The first part, which is the simpler one, is about my favorite subject, which is systematics. So when you're doing a PDF, you are complicating, right? You are opening up your observational space. You're extracting more information from the data. And then, of course, I assume that this increases a lot what types of systematics can kill you in different ways. And we don't have like 20 or 30 years of experience from this particular observable to control it. So the first part of my question would be, what are the ones that keep you up at night? And if you could give us like a qualitative tour of what are the things you worry about when you're doing those measurements. But then the second part of my question is that when Miguel asked about the observable, when you talked about, for example, super and sub-Poissonian noise, it made me think that when, for example, we measure angular power spectra, we never really do complicated stuff with the noise. We assume deterministically that is constant. We estimate the value from the data. Sometimes we can use it this constant level as a free parameter to try to calibrate it together with the measurements, but we're not really looking, this is an example of what we're not looking in more detail. So that made me think about my question coming from the other side. If you take your observable and you combine with traditional observables, now you're more sensitive to more systematics, but then if you can model those systematics, you might self-calibrate stuff that might be killing the 2-point guys. So for example, you could calibrate a non-Poissonian shot noise that might be now in your big MCMC model. But then you have to calculate covariances, cross covariances, you have to have a model for that, and et cetera, et cetera, et cetera. And it's like a big can of worms. So the second more complicated part is have you thought about these kinds of things, and what are your thoughts on that? And maybe if other 2-point people like Martin, who talked about 2 points, have opinions, so it would be nice to hear some thoughts on this. Thanks a lot.
Yeah, thanks a lot. No, this is really important questions, and as far as I understand, there's roughly 2 questions, and I'm going to answer the second one first, because the first one actually relates to something quite closely that Martin in his talk was also talking about. So first about this kind of race that you described of course you open up the observational space, so you're going to have more data, but of course you might also be worried that now you need to model more systematics, and it's almost and it's from the onset it's not clear what is going to win basically, so even for us, it's not yet 100% clear. So we, in the Dark Energy Survey year 1, we had an analysis based on this type of formalism, and we managed to get constraints out that seemed to be consistent with the 2-point function analysis, but still gave us more information on stochasticity and on skewness of the density field. So there it seemed to work, but of course this can break down in the future. And yeah, in the second point, I'm going to tell something about the systematics, which I worry about. But in terms of this kind of synergy that you were talking about, maybe it can even help the 2-point statistics. And that is really what I think is the main benefit of this. So I think on the long run, it's not so, at least I personally feel we shouldn't try to like measure the PDF on 20 different scales and then completely replace 2-point statistics. But I think the PDF could be an interesting anchor at one particular scale to help the 2-point statistics. For example, if you just think of, for example, the bispectrum and the power spectrum, then sometimes there is these kind of consistency relations that certain effective field theory parameters that you need for the 2-point function, you can actually constrain if you know the 3-point function and things like that. And there I agree. This is my ultimate hope, that the 2 can be combined and exactly help each other in this way. Now regarding the systematics, so one point that I worry about is you can have an arbitrarily complicated bias model. And I think at some point, you're almost introducing too many parameters. So you can have shot noise, and then you can have arbitrarily many parameters to describe shot noise and its density dependence and scale dependence. Then you have bias, you can describe its scale dependence, its density dependence. But at some point, I think the real amount of parameters is just a cut through all the potential parameters that you could think of. For example, if you have on very small scales a nonlinear bias, then at larger scales, this will actually look like a stochasticity and things like that. So this is something that I'm worrying about quite a lot. How can we be efficient with our parameters there? Now, another thing that I'm worried about, and this is where I'm coming to Martin's talk actually, this is observational systematics on the sky, and there are spatial fluctuations on the sky. So if you just look at the sky and have a galaxy sample, then you're going to have depth fluctuations. Seeing is going to be different, sky brightness and whatnot. And this introduces a lot of artificial fluctuations into your density field, into your galaxy density field. And for 2-point statistics, you can exactly use these kind of methods that Martin was also describing, where you try to fit galaxy density as a function of your foreground systematics and have a weighting scheme which fixes your 2-point function statistics. But for PDFs, it's a bit more complicated, because there you're not just having to fit the mean relation, but in principle, you would even have to understand the PDF of the systematics. And so for DES year 1 data, I've been working with a master student here in Cambridge, and we have looked into exactly this and looked at DES year 1 data and how the PDF of systematics influences our stuff. And there it wasn't a big deal. We found that it didn't impact our results significantly. But for the future and for the kind of precisions that we're aiming at the future, this is the thing that I'm most worried about, I think.
Very good. Jorge Norena wants to ask a question.
Yes, I have a couple of questions. One for Oliver again. So you were talking about constrained non-Gaussianity with this method, especially if you have 3D information. But will you be able to tell something about the shape of non-Gaussianity in the sense, or is it just the amplitude that affects your PDF?
Yeah,
and,
that's
yeah.
Oh, sorry.
No, my other question is for Martin, so I can ask it later.
Cool. Yeah, so that's it's if you just stay at one scale, it's indeed quite difficult to distinguish between different shapes of the non-Gaussianity, because what you're primarily seeing, you're seeing two things. You're seeing the skewness of the linear density field at a particular scale, and you're kind of seeing the derivative of the linear field skewness with respect to a scale. And the first thing can only tell you about the amplitude of the bispectrum. The second thing can tell you a bit about the slope, or about the shape of the bispectrum, but also not so much actually. So there is a strong degeneracy between, so a PDF at just one scale would have a hard time distinguishing between different bispectrum shapes. Yeah.
You had another question, Jorge.
No, the other question is very naive for Martin. So, or anyone in the audience who can point me. So you can use lensing to break the degeneracies between halos, etc., with bias, for example. So I was wondering if there is any systematic study that did analyze non-Gaussianity, which is the thing I care about, to break the degeneracies that appear there in the 2-point function, but also if people have looked at cross 3-point functions.
No, I can't. I don't have anything right now in mind that use the cross correlation between positions and shapes. You mean?
Yes, because hopefully one can break the degeneracies that appear when you care about non-Gaussianity.
Okay, I think Miguel has another question.
Yes.
I can look into the literature and point you to something.
I interrupted you.
Right now, but it's a very good question. I mean, trying to look at FNL from the point of view of galaxy lensing combined with clustering.
So I have a question also for Martin, but I don't want to be the only one asking questions, so I encourage the audience also, please ask. So Martin, in your talk, you're talking about, there's two things in your talk that I have the same question about, which is, you're talking, for instance, about this red magic and the maglim groups of galaxies, right? And basically the maglim has over 3 times the amount of galaxies. And but my question is, when you go to group catalogs like maglim, which is, I understand it to be more empirical, that you're trying to fit an A and B parameters in order to define the catalog itself. In the end, this is calibrated with simulations which are themselves assuming lambda CDM. So my question is, how much you think when you start to put things which are too empirical that you might be cooking lambda CDM in the data itself? So this question for me appearing on this maglim and also in your self-organized self-organized catalog, self-organized technique, sorry, the SOM. So how much is this bothering you, or you don't think this is too much of a problem because it's too astrophysical, it's not cosmological?
No, I don't. No, it's not. These are calibrated on the data itself. So we define this maglim sample is calibrated on the data itself. It's not necessarily assuming lambda CDM. So there is no cosmological model assumed in defining the sample. And basically the only thing with the optimization that we do is like selecting a sample that is what we cannot do. What we would like to do also is to try to select samples in terms of intrinsic luminosity, but we cannot access to intrinsic luminosity. We only have observed luminosity. And so in practice, what we do is to select samples that are brighter and brighter as you go to lower redshift. But they do not assume any lambda CDM. Neither the SOM PC work. They don't. It is true that the SOM PC uses simulations to calibrate to make sure that the method is not giving you any biased results. But it will not be sensitive to the cosmology.
Did you, just to finish, did you test or you plan to test this SOM, for instance, in different? I mean, now you have simulations which are either including baryonic effects or including low lambda CDM physics like modified gravity. Did you plan to test this there just to, as a cross check that you will lead to the same results?
For the SOM PC is basically a method to compute photometric redshift. So that will not depend on the cosmological model, not to first order, for example. Then what you can do is to try to run your pipeline to the right cosmology on simulations that have different cosmologies and different physics, like if you have baryons, etc. This we are limited in a way. We don't have. It's very hard to have simulations that are the size of DES, for example, that also has these alternative cosmological models. Most of the work is done on lambda CDM simulations. So there is really a lack of. Going forward, I think it's very important to also develop these very large simulations for alternative cosmologies, no? If that's the question. But the way to estimate photosis do not depend on the cosmological model, basically. So that's what we think.
Very good. Enrique Rubira has a question.
Yeah, my question goes to Jorge Norena. So in your talk, you say about like the constraints you expect to have in FNL using, I think you said using only linear theory. So how much do you expect to improve it if we consider like, you know, loop corrections and those things?
So yeah, in the work that we did with Matteo Biagetti, who is also in the audience, Asede Moradinejad, Vincent Dejac, and Emiliano Secusati, we used simulations that were run by Matteo. And so we tried to extract the FNL that was an input on the to the simulations, just as a check of the model and if whether these models introduce some bias. But it can be a first step for a thorough analysis to see whether you will be able to extract FNL. And so we didn't use linear theory. We used a three-level. We used a three-level for the bispectrum, which means second-order theory. And of course, this can be improved. We pushed that a bit hard to K of 0.2, which maybe is too much. I mean, maybe it's too small a scale. And there is an argument to be made from this to go to the one loop bispectrum, even if you stay at the one loop. For the power spectrum, we use the one loop power spectrum. So there is an argument to be made to go to the one loop bispectrum, even if you don't do two loop power spectra, because in this way you can really push the bispectrum to smaller scales and gain a lot of signal. This is what we find. And we do find some bias on our model induced by this fact that we use the three-level bispectrum. I don't know if that was your question. I hope I.
Yeah, but in terms of numbers, like you have any expectations, like how much it improves FNL?
Well, so let me share my screen again, but I closed the plot. So this can be seen from the plot that I briefly showed. And yes, let me share the screen again. Yeah, so here, this is the plot. So you can see that the bispectrum helps a lot in breaking the degeneracies that are in the power spectrum. And you see that it's a large improvement. Now what happens if we instead fix the one of these bias parameters that are degenerate? We fix it to a measured value, because in the simulation you have access to matter, so you can do a cross between halos and matter and do measurements. So if we measure this B phi, which is the non-Gaussian bias, the bias induced by non-Gaussianity, we measure that we fix it to a measured cross, we get a model which we get constraints which are biased. The simulation has FNL 10, which is the dashed line, but instead we find that it's compatible with FNL 0. And we think that this bias mainly comes from the fact that the model for the bispectrum, which is helping to improve the bounds, is not very good at scales of 0.2. And you can see that you can greatly improve. I mean, you can see that the bispectrum really contributes, and you can really improve your constraints on FNL by including the bispectrum if you push it to the scale of 0.2. Instead, if we stay at a scale of 0.1, the constraints that we get are similar to the red constraints. These red constraints are with an informative prior, but if we instead stop at 0.1, we get a similar constraint for the spectrum as this red constraint. It's not here on this plot, but that's what we get. So you see that there is really a lot to be gained if you go to smaller scales, where you have to improve the model.
I mean, I have a question. I have a question about constraints on non-Gaussianity with large-scale structure, and it's a kind of a general question, but it's the following: is there a disconnect between what's going on in the data analysis and theory, or what we think we can do in the future? And the reason I ask is I was recently trying to figure out what were the tightest constraints on FNL from large-scale structure, and if I'm not mistaken, the last published results was about 5 years ago from BOSS, and they had a problem. You know, after that, they've had consistent problems with systematics. I think they've overcome, EBOS has overcome that, but it seems that it is much, much harder to measure FNL and non-Gaussianity from large-scale structure than we're willing to acknowledge when we work out the theory and do these various things. So the question I put to you is, how do you absorb this fact? How do you incorporate the fact that the observers are having difficulty in extracting FNL into these models and into these forecasts?
Well, I don't know if I'm the best person to answer this question because I'm more on the theory side. But what you hope to do is to try to do not a forecast, but well, I think that's why the exercise we are trying to do with these collaborators is interesting, because we are not doing a Fisher forecast. We're really trying to extract an input FNL from a simulation. We are still a ways off because we are only in position space and we don't have survey masks and these kind of things. So I think by trying to do it, we will learn what are the difficulties and try to improve on or look for techniques that help with this. Yes. And it would be nice to interact more with people involved in the observations. My collaborators are involved in Euclid. And if I overcome some administrative hurdles, I will be able to join the LSST. So hopefully, yes.
I see.
Yeah, so just for the record, Matteo Bigetti here. I think the last measurement is from EBOS on last year. Just for the record, there is a paper by Emanuele Castorina and others. I think they get constraints that are still not competitive with Planck. But yeah, so with surveys, also we should distinguish what type of non-Gaussianity we are talking about. And the discussion would go too long, but it's true that for some reasons, depending on FNL, large-scale structure has more problems to deal with, basically non-linearities that in CMB there are not. But then the hope and the knowledge is that the number of modes that are available will compensate for that at some point.
I think the thing I was thinking of now was the scale-dependent bias calculation, right? And that's the thing where they've really run up into problems in trying to harness the largest scale modes, which are also the cleanest modes.
Yes.
I think the paper you're talking about, is it a bispectrum constraint?
Yeah, I don't know if Jorge, but yeah, so it depends. Yeah, so if you want to talk about local non-Gaussianity, I think in our paper, but not only in our paper, also before it, we show that combining the power spectrum and the bispectrum is essential. Otherwise, you may claim some detection of a 1/Q² behavior at large scale in the power spectrum, but that's it. That's what you can claim, and that's it. So the bispectrum breaks the degeneracies, and we show that by going to small scales, it helps because you kind of are constrained to calibrate your large scales also with your small scales with a consistent model, which goes to which predicts both regimes. So then you gain a lot, and then it's true that you still need large scales. So as long as your survey doesn't go to very large scales, you are not gonna constrain competitive with the CMB. But and also, yeah, so observing large scales in surveys is difficult because of the window function and so on. So that's the thing that is been already discussed in Euclid as well. So people is taking this in hand, yes. So
if I can chip in real quick, this is Alex Ferreira here, still on the topic of FNL. So Pedro, you were asking about observation systematics, like difficulties in measuring power spectrum on large scales. Yeah, in this Castorina et al. Paper that Matteo mentioned, they have some discussion on systematics. I forget exactly what those are because I'm more theory minded. And in that paper, it's only the scale dependent power spectrum that they look at. They don't look at bispectrum.
Bispectrum.
The theory
Okay.
side, though, two things that were not mentioned in this discussion, which I think are super crucial, is first of all on including the bispectrum. So although it's true that, of course, going to smaller scales improves the signal to noise, it's also true that most of the analysis, if not maybe, will assume Gaussian covariances for the combined power spectrum plus bispectrum. And this will, of course, degrade the signal to noise a little bit. And I don't think it's well known how much of a degradation in FNL we get after we include all of the contributions in the covariance. And another big uncertainty concerns, which is something that Jorge already alluded to, concerns the bias parameters. So most of the analysis assume the fixed relation between B phi and B1, B phi being the coefficient of the scale-dependent bias. And we have some idea of what this relation is for halos. It's fair to say we have no idea what this is for real life objects like galaxies or quasars. So that's also another main theoretical uncertainty. So
yeah, the second one, the bispectrum can really help, right? Because it can really break these degeneracies.
Yeah, I think it depends, because in your paper you still assume
we still assume a Gaussian covariance, as you say, but
yeah, but even then you still put some. Your uninformative prior still put some bound, if I remember correct, on some of the parameters. B phi delta is not completely free. And I could argue that even then there are some degeneracies that can degrade the constraints. But you're right, adding the bispectrum in general can help. But yeah, on the bispectrum level, we still need to understand what's the impact of the covariance, I think.
But from a purely observational, so just something very quick. I think it's, yeah, from a purely observational point of view, what you want to do is to add power spectrum by spectrum, but I think it's fair to say that the analysis of bispectrum is quite complex, and we are not yet at we haven't to the standard at which the power spectrum analysis is. So if we want to measure neutrinos, or if you want to measure FNL or other primordial Gaussianities, then we will need to first bring the analysis of bispectrum, even in pure lambda CDM, to a standard in which is not yet.
Mm-hmm.
And that is also critical for the analysis of systematics, because they will appear differently in power spectrum and bispectrum. And you won't need to be just relying on the very large scales that are, it will be always susceptible to some kind of systematics if you just rely on that.
I had some people putting their hands up here. First of all, there's Mustafa. Let me just say who it's. First of all, it's going to be Mustafa, then it's going to be Caroline, then Rogério, and then Olivier.
Yes, hi, my name is Mustafa Ishak from the University of Texas at Dallas. Mine is rather a quick comment or response to Jorge. I think you asked if there are any systematics at the 3-point level that you would be interested to hear about. You mentioned also LSST. So one of the systematics, I think, at the 3 points, at least for certainly for lensing and large-scale structure, is the intrinsic alignments of galaxies. At the 3 points, they are also as strong as at the 2 points. So those are worth keeping in mind. It was more of a comment. Yeah.
Very good. Who's next? Caroline?
Okay, so my question is for Jorge Norena, and it's about the last part of your talk when you did that reasoning about the mode coupling between the potential and the density field, and how differences between the Newtonian and the relativistic scenario appear. I didn't understand very well your reasoning, so if it's not going to take too much time of the discussion, could you go briefly through that again? Because I'm very interested in the relativistic analysis of the bispectrum. So
yeah, sorry, I didn't understand the question, but my main focus is the degeneracy with FNL, of these relativistic effects with FNL. And since relativistic effects have some terms that go like the potential, this means that when you cross-correlate with, when you correlate, you take density, you will get potential density, which looks like a 1/k squared in principle. And so this would be degenerate with FNL of order 1. And something I showed is, so we did a weak field calculation, which is much simpler than a full GR calculation. And we found a few differences with the Newtonian perturbation theory that people didn't explicitly state before. So we found that there is a contamination on the bispectrum of FNL of order a few that goes with redshift in the same way as the primordial contribution. So it's completely degenerate with a primordial contribution. So this has to be accounted for, cannot be eliminated by looking at the redshift dependence. And we noticed that in order to get it right, you have to set second order initial conditions, which people are not currently doing for simulations. So I don't know if that answered your question because I didn't completely.
No, yes, it was somehow in this direction because there is this need to go beyond the, I don't know, in simulations to go beyond the Lagrangian perturbation theory if you want to do things properly from the initial time of your simulation and involve the primordial non-Gaussian initial conditions. So I just wanted to see if that was the reasoning behind, and thank you.
Okay, I think we now have Rogério and then Oliver. We're 2 minutes away from the cutoff time, so please be quick.
Okay, two quick questions then. In the simulations that Jorge mentioned, one, do you have baryons or not?
No, we don't, but Matteo can answer the simulation questions much better.
Okay,
we
so
don't have baryons.
That was the question. So would you expect baryons to change the small scale analysis?
Sure. Small scale, yes, but FNL mainly comes from large scale, right?
Okay, and one really quick question again, how can you separate non-Gaussianities from primordials from nonlinear effects in GR?
So in GR, you cannot. This is precisely the point we are making. So there is in principle, no way to separate this contribution at the initial conditions, which comes from nonlinearities in the primordial plasma, etc. Which you compute. There are already codes available to compute them. You cannot separate them in principle, but they are computable. So you know what you will get. They are perfectly computable. So, yeah.
Thanks.
Okay, Oliver.
Yeah, just also a quick one, touching upon a point that Alexandra made, and I guess this goes to Martin or anybody else who knows about this. So very often galaxy bias seems to be much simpler if you have halos of a well-defined mass bin and maybe even concentration bin. So for example, there's a super tight correlation between linear and quadratic Lagrangian bias for dark matter halos. But then, as Alex said, as soon as you have actual galaxies, all these nice kind of relations seem to break down. And yeah, this is somewhat of a general question, whether is there any good ways to recover this analytic knowledge of consistency relations that we have for halos once you look at galaxies?
Do you mean to define samples in a way that you recover those relations, for example?
Yeah. Or well, or is there, I mean, in a sense, since we know these relations hold on the level of halos and galaxies populate halos in some way, is there useful methods to just incorporate how your galaxies populate different types of halos into your modeling, basically?
Yes, so this is something you can always do, no? If you can always convolve with your HOD these relations, and I don't know any paper that has done that and show that actually works in simulation, for example. So that you measure these relations in simulations, in galaxies, and there you can also measure the HOD exactly, and you can see whether propagating this HOD works well or not. But in practice, it's very hard to know the HOD of the galaxies that we observe anyway. So in DS, as you know, we've tried to do this and it didn't quite work.
So is there no like generally accepted parameterizations of HODs in data analysis, or?
Say that again, if there is.
So if is there generally accepted ways of parameterizing these HODs that people have applied to data, or?
Yeah,
because you don't know the HOD, right? You just need to know how it's expected to be shaped, basically.
Yes, exactly. You need to know the parameters of the HODs.
Yeah,
how they change with redshift and everything. Yeah.
You also need to know the variables, right? You're talking about just the HOD as a function of halo mass, which is already a simplification, right? If we bring in considerations of assembly bias, that only complicates things.
So yeah,
Okay, I think we need to wrap up. We're going over time. I'm going to thank the speakers, the poster presenters, and all the people who took part. This was a very active session, and I hope this is a model of how things will work for the rest of the week. See you later.
Can I just send a last message? Some people are having trouble in the website to open the videos and the talks and the PDFs. There's
They have
not
to
the only
open a
thing,
new
not
tab.
Exactly, open in a new tab. There's like a bug in the system. You just open in a new tab in your browser and it should work. Okay, so that's beyond Google problems. It's beside all the Google problems. Thanks, Pedro.
Thank you very much.
Thank you. So see you at 2 p.m. São Paulo time.
See you guys. Bye-bye.
Yes, see you guys.
So Miguel, what do you think?
Yeah, it was good.